And I deliberately went a little bit slower than I had originally intended with the earlier part, but I think the context of a long workshop like this, where you're going to be here working for today's kind of merited taking a little bit more time to explain a few things rather than just blasting you with a really, really fast-paced demo. Sometimes I do all that I just did in about 10, 15 minutes, but it's a little bit like, and I don't think it conveys the ideas as well. So let's continue. We've already mentioned this idea of reproducibility in research. And this is a quote that I've used many, many, many times. Some of you may have seen it either from me or from others. It's a quote from Buchheit and Donahoe. And I want to point you to the date of that quote. It's a quote from 1995. I actually want to read it. An article, the emphasis in there is not mine, it's in the original. An article about computational science in a scientific publication is not the scholarship itself, it is merely advertising of the scholarship. The actual scholarship is the complete software development environment and the complete set of instructions which generated the figures. So David Donahoe is a statistics professor at Stanford, and he was writing this as part of a paper that was the manual for a package called WaveLab, which was developed by folks in his lab for wavelet research. He's kind of a statistical numerical analyst is what I would call David. And even though it was on top of MATLAB, which is a proprietary product, it was a sensible choice in 1995. He did make WaveLab itself was open source, and him and his students and postdocs published this as a complete package where when you downloaded WaveLab, there in the manual section in the paper, there were directories called Figure 1, Figure 2, Figure 3, and you could type whatever, make or whatever, run some script, and it would reproduce everything. And he was a strong believer in this. This was building off of the work of somebody else also at Stanford called John Claerbout, who was a geophysicist who had basically baked into his lab the idea, not out of altruistic or epistemological considerations about science and openness and whatnot, but purely out of productivity interest, had built into his lab the idea that every grad student who worked would build their research as basically a package where they could type make, and it would produce everything, and it would recreate every figure, everything that they did, so that when new people came into his lab, they wouldn't spend the typical pattern of many research labs, which is you spend the first 2 or 3 years getting back to where the grad student who's now backpacking in Indonesia and left a zip drive somewhere in the previous office, and when the movers came in, nobody knows where that USB thumb drive is, getting back to where they were so that you can do a little bit of new research in the last frantic year of your dissertation. Instead, he said, I want people to come in, they grab the previous stuff, they type make, it works, they spend a few weeks understanding how all that works, and then they start doing the work. And in fact, he built something called before Linux distributions were a thing, called Unix for Geophysics, which was basically a Sun distribution of Unix with all of the packages that they use. He was a geophysics modeling person. To basically on Sun workstations install Solaris back in the 90s, install Solaris with all of their packages and be able to build that off. And Donahoe and Buchheit kind of picked up on that, on those traditions from Claerbout and articulated this really, really well. I strongly believe in this as kind of a very good way of capturing what we should be doing in research. Unfortunately, today, most papers are PDFs, and you read them, and if you want to actually replicate the work that is there, good luck. Did the authors make the code available? Maybe, maybe not. Did they make the data available? Maybe, maybe not. So hopefully we can begin now with the tools that we have at our disposal today, get to the point where we can build more towards embodying this ideal without having every single one of us have to become a professional software engineer. Because that's the other thing. We can't, if we raise the bar on these demands so high that you can't do any scientific work, it kind of defeats the purpose of the whole enterprise. So I'm going to be talking a little bit about things that I did last fall at Berkeley. I taught a course called Reproducible Research, Reproducible and Collaborative Data Science, Stat 159. It was a course that was scheduled with 2 lectures and 1 lab a week, listed as a statistics course, but open really to anyone with fairly basic foundations in computation and statistical modeling. I had about 50 undergrads and 10 master's students, or not 10 grad students, had a couple PhD students. And a lot of credit goes to my wonderful GSI, who did an incredible amount of work. Eli Ben Michael, PhD student in stats. This was a course that had people a little bit from all over. Because it was listed in stats, obviously there were more statisticians than from other departments. But we did have a good mix of people, including folks like nuclear engineering PhD students and civil engineering ones. And what I tried to do was to sort of cover these notions of reproducible research in a whole semester at the sort of what level. What are the ideas and the concepts and also the ethical and epistemological reasons for considering reproducibility of computationally based research, kind of a core foundational part of science. Trying to frame the problem from a variety of angles, framing it as a practical problem, as an ethical one, that making our research accessible to others is part of the commitment that we have to society who funds our research, and of engaging the public with our work, and also of making it accessible to those who have less resources. And finally, as an epistemological one, basically asking the question that if we make our scientific research, if the purpose of science is to sort of open the black box of nature, doing that with a process and tools that are not themselves open and available to others is kind of an oxymoron. And then finally, learning the actual skills and habits to make this a daily practice. Because very importantly, a lot of this work was about turning this into just the way you work, right? Reproducibility is not a publication time concept, okay? By the time you're happy with that PDF that you're submitting to the journal, if you say, okay, now that we finally, we hit submit. Okay, tomorrow I'm going to clean it up and I'm going to make this project reproducible. Not going to happen, okay? Not going to happen. Either you do it from day one as a daily practice, or you just don't do it. And so the idea was to basically build a combination of skills, and I want to emphasize that this is a choice. Perhaps one good way to frame this is what is called a pattern. This is not the answer, but I think the pattern is the right pattern. You may choose in your work to change any one of these specific things. It doesn't matter. You may choose to skip one of them. You may extend them. But the pattern, I think, does cover important things. Version control, using Git and GitHub as tools for storing your code. Programming with an open language. We used Python in this course. You could be using other tools. But basically scripting and programming your way through. Automating everything that can be automated. We used Make. Make is an old tool. It's quirky. It's kind of a pain in the neck when things get complicated, but it does the job and it's always available and it's a good starting point. You can choose later to use other process automation tools. There's been many more modern attempts at replacing Make. Interestingly, no one has succeeded. A data analysis stack on top of your basic language. In this course, we used a little bit of some of the same standard tools that you'll be learning here. Documentation as a core part of the process. We used Sphinx as an everyday tool. Sphinx is the tool with which the Python documentation is itself built. It uses restructured text as its input format and it produces HTML output, but it's actually a very extensible tool. And in fact, in this course, we used Sphinx extended with Markdown input and Notebooks input, so that basically you could write either restructured text or Markdown or Notebook as the situation warranted and assemble finished outputs into Sphinx. Testing. Testing as an everyday practice. Untested code is broken code. Repeat after me. Untested code is broken code. If you don't have tests, you don't know that it works. Now, tested code isn't correct code either. It's not, unfortunately, it's not a sufficiency argument, but it is a necessary argument. continuous integration. The notion that once you've built your stuff on top of version control, once you have scriptable tools, once you've tested your stuff, then the machines can help you. The machines, Travis is a machine, it's a system to do continuous integration. Continuous integration is the notion that as you make your changes, as you do your work, something picks that up and tries to basically run every possible battery of tests. Obviously, you have to tell it what to do, but it tries to run for you as you work all of the tests that you tell it as you go, so that as you keep working, something is continuously kind of assembling your system for you in the background. And so it's the idea that by the time you come to GitHub and somebody says, I want to make these changes to your project, here's my pull request with these small improvements, that code that they're proposing has already been put in through the paces for you by a system, Travis is one of them, there's others, that will run that code inside of your system, will run every possible test that you've told it, will try everything, so that you can focus on discussing, do we want this? Does it do what we need? Is it a good idea? Is it written the way we want it to do? But everything else has been validated for you, so that you're never, in a situation of asking, oh, shoot, for the last 6 months we've been merging a bunch of code. Now let's see if it works, right? Because that is the kind of insanity that we used to do. But it really is insane, and it's very dangerous. And we're going to wrap up with something called Binder, which is a project that actually came out of neuroscience, out of Jeremy Freeman's lab originally, who's now at the Chen Zuckerberg Initiative, to try to bind all these things together into a neat little package that you can hand out to others. So in the course we talked, and Ariel, is there going to be work on Git and GitHub at here? Kind of a little bit of
We did a little bit yesterday.
Yesterday? Okay. So we did that with the students. The idea was Git is not something that you learn as a special thing. You don't learn to do email, right? You do email every day. Yeah, sure, at some point you have to learn a few things, and maybe you get a new client and you learn a new set of keyboard shortcuts or a new feature, but the point is it's something you do every day. And so the course, everything was done on GitHub. The students had to clone the class repo. I would be in a coffee shop next door to the classroom, 3 minutes before class, making changes, git push, git push, git push, and getting the builds up so that the lecture for the class in 3 minutes would be up and ready up on GitHub. It was built on Sphinx, and the students would have access to all the materials from GitHub. This is kind of the equivalent of making the difference between brushing your teeth and a root canal, okay? Which hopefully we can all agree that we'd rather brush our teeth than have a root canal. And Git is kind of that moral equivalent. So not only was the class content based on GitHub, every project that we did was run using a system called GitHub Classroom. It's something that Git offers for education. It's not great, it's not perfect. I think it was a prototype that they built with a relatively small team, but it does get the job done. It does help automate some tasks for creating homework. Basically, you can, as an instructor, you can create a homework template and then push it to the students, and they all get an individual link. They all get, effectively what it does is it does a fork of that one master repo for each student, but it's not they don't show up as forks, so you're not trying to like merge because it doesn't make sense. You do want to use a common starting point for everybody to do the work, but you're not trying to say everybody now merge back their answers. And so it basically kind of uses the underlying GitHub architecture, but presents it to you in something that makes a little bit more sense for classroom work. But the point is, by having the students do their homework, the class projects, the class activities, the class content, everything every day with GitHub, then these things become second nature, right? It's kind of drilling into people the point that Git is a tool that you use for everything you do. As much as you type make dir to make a new directory, a new folder for something, you type Git in it to basically turn it into a repo and do something version controlled with it. explicit dependency management. So the class was structured where the class repo had an environment YAML file. So I basically, have you discussed environment files yet? So environment.yaml is a file specific to the Anaconda system, but there is moral equivalence of it for just about every other packaging system out there that basically says, these are the dependencies for this project. These are the specific tools that we're going to use and the specific versions that we're going to use. And this repository uses these specific tools. And if you grab all this and you have these specific dependencies, everything that's in here should work. And we test that. And by making that explicit, right, and putting it in the repo from the beginning, I knew, and I didn't change it throughout the semester other than a bug, unless I found a bug and we had to change a specific version of something. The idea was we freeze this, and whatever the students are doing on their laptop, whatever other projects they have with a different version of NumPy, of this or that, I don't care. Because there is an environment named S159 Sphinx where they go, and when they use that environment, they have those versions of the packages, and those are the same versions that I have on my computer, they have on their laptops, that is on the hub that is hosted, that because they had stuff on their laptop, but we also had a hosted hub for them, so that everyone is known to be on the same page. And there's no arguments about, oh, which version are you using? You have a bug, and maybe it's none of that. Everybody is exactly on the same page, regardless of whatever else they're doing for other classes or other projects, etc. Automation and testing. So make as a way of life. If you do something more than once, so when we talk about programming, we say if you do something more than once in a piece of code, put it in a function, put it somewhere, and call it instead of copy-pasting it. Well, make is the moral equivalent of that for activities. If you type something more than once, if you keep doing something, make a command out of it and run it as a command that you can repeat. And the software carpentry, which is a project that has come out of this broader community of open science, it's a project for teaching computational skills for scientists. How many here have attended a software carpentry workshop or taught one? So some of you have, not too many. For those of you who haven't, I would argue that this workshop has a flavor of an extended, I mean, not these 2 hours, but kind of the whole 2 weeks is in the spirit of software carpentry. But you may still find some of their work useful. They have some wonderful reusable lectures on various topics, and I actually used their lectures on Make. The idea being that the students learn how to automate and track dependencies in their work as a natural and routine task, because it's very important. Once you've defined which tools you're using, once you've pinned down which dependencies you have, now you're beginning to do your work. And if you're doing it with a programming language, you can tell the computer to do it, but you don't want to say every time. You don't want to write some gigantic script that basically says every time I'm going to do this, run this thing, and it has to do absolutely everything, because everything in your case could actually be a lot of compute work. So what a tool like Make allows you to do is to define what pieces of computation depend on what. And so unless this has changed, you don't do that. So that as you run your computation, if you make a small change somewhere, you can tell it, do it again, and it checks what needs to be redone, and what needs to be redone gets recomputed, and what doesn't need to be redone, then it's just left alone. So it allows you to maintain a process where every time you make a change, you can say, go do it, and it's quick, because it tries to do the minimum amount necessary of work, while still letting you do things like, say, make clean, which means wipe everything out and start fresh if you need to do so. So the students learned how to do that. They learn how to do continuous integration, as I mentioned, with Travis. So it turns out that you can go to travis.org and actually say, for open source projects, I want to activate Travis. And what happens is you have a repository on GitHub that you tell it, I want you to be on for. And what happens is the following. You tell Travis, in that repository, you tell Travis what script to run as your tests. And whenever you make a change on GitHub, Travis will automatically go and pick up that repository and run the script that you tell it. Now, it's up to you to say what counts as a test, right? You could run one giant blob, you can run 1,000 little things. That part is completely up to you. It's not magic, it's not artificial intelligence. It's simply saying, you tell me what repo you have, you tell me how to put it together, and you tell me, once I've put it together, what you want me to run. But if you do that, then on every commit, automatically, every time you make a commit, it goes and picks it up and runs all those tests for you, and it tells you what to do. So part of the point of this course was to show these ideas to the students in real-world practice with real-world tools and data. So we picked up a paper that was published in the Open Science Journal of the Royal Society. It was a paper written by 2 Norwegian scientists about wind patterns in Europe, and it was a historical analysis of about 100 years, statistical analysis of about 100 years of wind data in Europe. In this case, the point of the work with the students wasn't to try to understand the specifics of the research. It was to try to say, well, what happens if I have a paper where the authors actually did the right thing, in a sense? The authors, in this case, published a repo. So one of the 2 authors, Lacken, actually made a repo on GitHub that had a bunch of stuff, including data and figures, and a link to the paper. And if you go to the paper and you download the PDF of the printed paper, this is what it looks like, formatted PDF, blah, 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 some figures. This is what the notebooks on GitHub look like. Exactly the same figure. So they really did actually kind of go after the idea of Donahoe and Buckheit and Claerbout, right? Here's the repo, here's my stuff. The paper that I'm showing you, this is the code that produced it. You can download it, you can run it, these are the figures. Paper is from 2016 or so. So, students, go do it, right? Here's authors who gave you their code. It's all open source. All the data is there. All the papers are there. It's fairly new stuff from just about a year ago. Go. Reproduce it. Just get the figures. The exact same figures as the authors. Did it work? Of course not. Bit rot, weird little things, even after a year, even with authors who actually kind of did everything right, and it didn't work. But it was a really wonderful experiment because the students had to begin digging into understanding why was it breaking for them, what were all the weird little reasons why they couldn't quite get it to work. And it actually led to Tom Caswell is currently the lead developer of Matplotlib. He was visiting me, and we found one of the things that we were finding was this really bizarre 3rd-digit minor version dependency on which version of Matplotlib was being used. And like literally, on the there was a 3rd-digit change in the version of Matplotlib where at one point you got the results of the authors, and if you update it to a minor XYZ sub-revision, it broke. And it broke in a really weird way in that the figures still were there, but the legend was off. The data set, and actually a problematic error in that the legends was mislabeling the data tracks. So you had a legend where the labels in the legend did not correspond to the traces in the figure, an actually scientifically problematic and really bizarre bug. And by coincidence, Tom Caswell was visiting Berkeley, and I showed him this, and he said, I know what they did. I know what they did, and they're using some weird undocumented thing in Matplotlib and passing a dictionary and this blah, blah, blah. He immediately knew what was going on, and Tom Caswell actually made a pull request to the author, basically changing how the call was made so that this weird internal change in Matplotlib didn't affect the problem. And furthermore, we actually made a few other fixes. For example, we gave them an environment YAML file because some of the issues were version number changes. There's statistical, there's a little bit of bootstrapping being done in their analysis, and they were not pinning down their random number seeds. And so you had analyses where random number generators were being used, and every time you run it, you got slightly different results. Hopefully they're statistically consistent, but you want to start from being able to replicate the same results. Afterwards, you start asking questions, but you want to start from a known quantity, right? You don't want to be wondering on the first stage, this is already not quite what they did, right? Now what? And so we made some of those changes. There's one thing we could never fix. You're probably going to see a little bit of a library called Seaborn, and unfortunately, Seaborn has a hard-coded random number generator seed deep into its internal bootstrap in a place that you can't change, short of actually changing Seaborn itself. So there is one thing that you cannot completely replicate, and that's a problem with Seaborn, because it hard codes in its internal bootstrap its random number generator seed in a way that doesn't let you control it. So, but the point is, the students actually got a flavor of doing this with real-world data, with a real-world paper, and engaging with the authors and seeing the value of doing their research in this way in the open, where we actually were able to basically go back. It's not like we changed the science in this case, but it was a very valuable experience to see how you can interact openly with the authors. In this case, these are people we didn't know. I mean, these are Norwegian wind scientists. None of us know these people, and yet the interaction was really productive. And this is how, in the end, this fellow responded, rock on open science. And so it was a very valuable and very productive experience. My only concern is if I ever teach this course again, I need to find another example that works as well as this, because this one was beautiful, but now we kind of fixed it. And so I need to go finding a new example. As I mentioned, we did all of this on GitHub Classroom. So for those of you who end up maybe teaching at some point or who have to teach, if you want to do this, it's not perfect, but it's not a bad system. It lets you build, basically give students templates. They go out, they do their work, and you can give it a deadline. And then when they come back, you see an interface where you basically, this is for this specific project. These are all of the student teams who did it, and I can see all of their repos. I can see when they committed. It does have the advantage that there's no losing their work as long as they commit and push. It forces them to work as a team on GitHub because they themselves are working through GitHub, and we evaluated that they were collaborating on GitHub, that they were making pull requests against each other, etc. And what they had to do was take that project and add to it things like a proper environment YAML file, a proper make file that will actually create all the figures. And so they added these things to the original paper, including things like running the notebook at the command line. If you want to run a notebook, it turns out that a notebook is a tool that you can use from the command line to re-execute. And so in your make file, you can say Jupyter nbconvert. nbconvert is the tool that converts notebooks to things like, oh, you want to make a static HTML page out of a notebook, you want to make a PDF out of a notebook. Well, you can also convert a notebook to another notebook by executing it. And so it's a way of saying, I want to run my notebook pipeline in an automated way so that I can do it in Travis, I can do it as part of my documentation builds, etc. I can have my analysis pipeline have notebooks that I did interactively while I was fixing them and fidgeting with them, but now that I'm done with them, I save them, and they only depend on their data, and if I change data, I can just run the whole thing, and they just rerun. You don't have to keep opening everything manually and doing Shift-Enter until you're blue in the face. That's not the point of spending all this time building tools just so that you hit Shift-Enter into the deep of night, right? We actually do give you tools to automate this process. And then the way we tried to wrap it up, and I'm debating on exactly, we'll take a check in a minute on how far we're going to go on this. But what we did, and if we don't do it today, what I do want to encourage you, and we may either try later in the week, or at least I want to encourage you to think about this, was to actually do, in their case, they had to pick an original analysis topic, they had to pick their own data sources, and they had to build a project that included data, either put it on repo, either the data is included or at least linked if it's too big to include. It had to include code that had tests in it, so not just notebooks, but also standalone library functions that had their own automatic tests. They had to run the analysis of the project with well-documented notebooks, but more than one. I didn't want to see one notebook where the scroll bar is basically 1 pixel thick, because if you scroll it, it's like 10,000 pages long, right? That is terrible. You can break down an analysis project into various stages, and you link them in between what you do. And we practice this in class. If you finish the stage, you dump intermediate data structures, you dump them to disk, you version control them, they become your dependencies between notebooks. You use whatever format is relevant in your case, whether it's HDF5, please not CSV, whether it's HDF5 or domain-specific formats, something that preserves accuracy and doesn't have data loss problems. And then, often, this is something that I emphasized a lot in this class, is that often the right way to present a scientific result and idea is not the same thing as showing all the steps in detail, right? Because those steps are the things you have to do to get to an answer. They're all of the little wiggly details that you have to cover in order to understand a question. But you often, when you present this idea to an audience, you're trying to take a step back. You want to take a step back and you want to say, this is the problem we're looking at. And at this point, this data is relevant, and this is the figure that shows this, and we have this result. And there may be all of these side avenues that are important to assemble those things, but that other story, the advertising that Donahoe was talking about, still makes sense to tell in its own right and without all of the noise of the individual analysis steps. So it's not the idea that they should, if you publish something where they didn't write it as a full paper, but that they should actually stitch together those and turn that into a main thing, but they actually had to take a step back and write a summary narrative that would then pick up the right figures and the right things from those notebooks, but still tell a single story. You had a question?
Yeah, do you have a process of going about like all the analysis steps and tagging the things you want to have in the summary document? Because I feel like when I'm analyzing data, I have like, I'm going to try this way, then this, and this, and this, and then I have to figure out like, okay, what things do I actually want to put in the final document that people will be able to understand? And just wondering like what your process is of actually picking out the things and remembering where they are to having the final document.
That's a really good question. So I'll repeat it for the sake of the recording and those in the back. Whether I have a process or what is a good process for basically, as you're going through all of these individual analysis steps, to tag what are the pieces that should make up this larger kind of narrative and how to pull them back together. I have to say I hadn't thought about it as a process question, but it's a really, really good point. I think typically I've tended to do it in a very ad hoc way of sort of just keeping track of how the story is coming together and writing kind of basically the paper in tandem with the analysis steps. But I think we could definitely do a lot better on that front. I hadn't thought of that. It's a really good point to think about it as a question of the process itself. I just hadn't taken that kind of reflective step back. So unfortunately I don't, but it's a really good point. Any other questions?
I don't use R, but R Markdown does a very nice sort of render, and it pulls in sort of values and things like that.
Yes. So the question is, R Markdown does a very good job of letting you basically render results in line in the Markdown, not just as a block of output, but in the main Markdown. It has a syntax for pulling basically to say X is, and then you have a syntax to say X, but it's the value of X, and it'll put in place the value of X, so that you can actually, even the narrative itself can be pulling bits and pieces of results and data. We don't have a complete solution for that. Matthias Buissonnier at one point made an extension to try to do that, but we haven't completely settled. Part of it is we sort of took a big detour of years from the main machinery of the notebook into building this architecture of Jupyter Lab and now Markdown support and compute kernels and whatnot, all of them, in a way that could lead us to these questions. This has been in the back of our mind for a long time. Clean solution for this. I've had discussions with Ariel about this, I don't know, 5 years ago maybe. And I sort of feel like we finally, now that the dust is beginning to settle on Lab, we can kind of go back and ask these questions for better solutions for that. Because we know we don't have a great answer for it. I don't even know if Matthias's extension was a little bit experimental, and I don't even know if he's maintained it or if I haven't kind of looked at it recently. So the idea was they would write this main. In this case, they did it as a notebook just because I was trying to keep it simple. You could do it as a markdown file. You could do it as a LaTeX file. You could do it in Microsoft Word if that's what your colleagues want to use. That one I think matters less because the point is that one is a document. If you're more productive with other tools, that's fine, because that one shouldn't be, and I told the students this, that notebook should basically do nothing in terms of computation. It may have a little bits of code, but basically to read stuff like load an image, load a table, maybe, I don't know, compute a small summary statistic or something. But the point is the real work should be in all of the detailed ones. And this one is simply assembling that high-level story, maybe without the best process on how to tag that, but it is just assembling that story so it can be put together with whatever tool makes sense for you. In this case, they did it as a notebook and they converted it to PDF. The students had to build a repository with a proper makefile that had targets to run the code, targets to build it, targets for everything, with an environment YAML file so that it could be checked out and run exactly with the explicit dependencies. And it also had to follow sort of good practices of open source sharing. It had to have a README that explains the purpose of it. It had to have valid licensing conditions. How can others use this code? It's not just enough to put something out on GitHub if you don't tell others under what legal terms can they use it. So we had some discussions about licensing and sharing. It also things like git ignore and whatnot. As a starting point, I suggested that they follow Victoria Stodden's Enabling Reproducible Research paper that defines a standard, suggests a standard with licensing conditions for code, for data, etc. Victoria Stodden is faculty at UIUC, Urbana-Champaign, University of Illinois. She was a student of David Donahoe in statistics, so she's a statistician, but who also has a legal background. So she's a really interesting scientist who has both a statistical background and a legal background and has done a lot of work at the intersection, basically, of computational research, policy, and reproducibility. And this paper defines, basically, a set of conventions on how to make your work reproducible and more accessible. This process is a process that you can choose to change. I think of this as a reasonable starting point. Any of these things we can argue with. You can choose to do things differently at any of these points. You can choose to use R Markdown if you prefer. You can use different tools for any of this. But I think the overall pattern of doing this is a pattern that can be followed, that students were able to follow, and that does lead, I think, to significantly better outcomes. And so I think it's a decent kind of standard playbook for reproducibility, not necessarily as the right answer for everything, but as a sensible, decent starting point that you can take. And the students did. This is an example of a project from one of the students who wrote. They put a repo, and they learned, for example, that they had. This was a pattern that we followed in class. There was a data directory with all the raw data. Fig is the directory where all the intermediate figures go, including many figures that may not end up in the main narrative, but all figures get checkpointed in there. Results is a directory that contains intermediate data structures and intermediate results that, for example, allow you to rerun the last notebook without having to run everything from the start. So all of those things are in there. It has a README, it has a proper license file, it has an environment, it has the various analysis notebooks, it has the main.ipynb, and it has a README that explains what the purpose of the project is, what the conditions are, and it actually has links to Travis. So this indicates that on Travis all the tests pass. So all the tests are currently passing. There's a tests.py file there, and all the tests are passing on Travis. And there's also a binder button, which we're going to see in a minute what that's all about. And they produced analysis notebooks. They produced code, pure Python code. They had to write not just notebooks, but actual standalone library code that they would import so that multiple notebooks could reuse the same function without copy-pasting. And so that they would get used to writing both notebooks and regular scripts. They had tests for those, and they would convert the main analysis one into an actual kind of properly formatted PDF. We didn't go very far. This was not a course on scientific writing. We didn't do a ton of work on that, but at least this was a project that had kind of the feel of an end-to-end paper with all of these elements put together in one. So I think it does give us sort of an actionable template for reproducible research with pretty good coverage of the tools and skills, and the why. The course itself was broad instead of deep. We covered all these things. We had basically lectures on everything I've mentioned, on Travis and on Sphinx and on YAML and JSON and Pandas and on NumPy and on scikit-learn and a little bit on everything. So it was kind of a hodgepodge of things. But for an audience like this, at the end they came out, for me, the fact that all the teams were able, this was one of the better projects, but everybody was able to produce this kind of artifact and all the teams were able to do this, for me was really satisfying, because in a sense it was exactly what Donahoe was and Buchheit and Claerbout were kind of saying, this is what we should be doing 20 years ago or 23 years ago. Here we have a bunch of undergrads who are actually, that's how they're getting used to working on an everyday basis. And I've mentioned Binder already a couple of times, and so I want to talk a little bit more about what Binder is. And a lot of these slides, by the way, are shamelessly stolen from a talk that the Jupyter Hub Binder team gave at SciPy, the Scientific Python Conference, just a few weeks ago, like 2-3 weeks ago. The talk, this is the link to the talk, and the video is already up on YouTube. So I'm shamelessly stealing most of their slides. And so the idea behind Binder is that these are all of the things that we need for doing open science. We need tools to solve the problem, all of the open source tools that we've been talking about and that we build. We need interfaces to help us, and hopefully Jupyter helps us with that. We need to communicate what we do. We need to share our work. We need to package it so that we can give others the starting point for the next step. And we need to do this easily without saying, well, by the way, on top of all that research work that you're doing, here's another 4 years of computer science and kind of Google level DevOps engineering that you need to do on top. That's what your next nights and weekends are going to be for the next 5 years. That's not fair. That's not sensible. We can't do that. So we're trying to support reproducibility, unpacking it sort of in two different ways. We can talk about technical reproducibility in the sense, if you have the right team behind you and all the skills and all of that stuff, yes, you can do this. Or the more practical one, which is, can everyday scientists do this as a matter of routine? Can we turn this into a matter of routine? And this is what we're trying to achieve, is making this the standard practice for everyone. And so for that, it means we want open tools for analysis and visualization, whether they're Python tools or R tools or Julia, etc. We want environments for the work, the analysis, the authoring of the documents, whether it's RStudio or Jupyter. We want tools for the sharing of our results. And the last stage, so we've talked quite a bit about these three. The last stage is we want a way of giving others those artifacts, right? We want a way of giving others that whole work that Donahoe was talking about, in the way that I can give you something and click, and you're working with it. And for that, the last few years, the software industry has built something called Docker. Docker, who here has heard of Docker in one way or another? Many of you have. Not all hands went up. So for those of you who haven't heard of Docker, Docker is a technology, and I'm oversimplifying dramatically, but it's basically a technology that allows you to kind of package something that's kind of like a virtual machine, like a little mini operating system, into a file that you can ship around, and it follows a certain standard. And there's a tool called Docker, right, that takes that file and runs it. That file represents always a Linux container, a Linux operating system, because you basically have to package the core of the OS and ship it around, so it has to be open source. But it is now natively supported, even at the very low levels of the OS, on Mac, Windows, and obviously it works on Linux. But the point is, it works really well on Mac and Windows. As of Windows 10, the kernel on Windows has specific support to make it very fast, and the same on Mac as of Yosemite, I think. And so you take one of these things and you type a command, and you're running that. Basically, you're running that computer on your own machine, and if it's a small thing, it's blazingly fast. You effectively boot a Linux kernel nearly instantaneously. Obviously, you can't package, say, Microsoft Word or MATLAB or native Mac GUI into Docker, but you can package anything that can be run as a Linux process internally. You can package it. So it's a very good way of packaging computational processes or things that serve web UIs, because you package it, it spits out a web port, and then you talk to it with your native web browser client. So we're back to this notion that by having chosen web architectures for science, we piggyback on what the software industry has been building, which makes sense for software development reasons and kind of cloud industry deployment reasons, and we can basically plug scientific interfaces on top of that engineering work that the DevOps crowds of the Googles and the Amazons and the Microsofts of the world have built under the hood. So an important point is, not that I need to belabor it, either coming from me or to this audience, that all of this is open source and community driven. And this is a little bit of a summary of what the current version of Binder is. There was an earlier prototype by, as I mentioned, Jeremy Freeman, neuroscientist originally at Genelia Farm. And today, what Binder does is it uses a technology called Kubernetes, which is a tool to take those Docker containers and easily deploy them in the cloud. The whole point is that we don't need to get into the specifics of what that is. You are neuroscientists, you're not necessarily software engineers, and so you shouldn't, if you're interested in that, you can learn about it, but you shouldn't have to learn about all of this to do your scientific work. It uses tools from Jupyter, but I'm going to get back in a minute to the point that it's not specific to Jupyter. So actually with Binder, you can use a pure R workflow if you want. And it's really aimed at scientists, educators, communicators in science. It's not aimed, we're not trying to make the job of engineers at Google easier. They know what to do, and they have the resources to do what they need if they need to, right? This is a tool for packaging scientific analysis workflows and education and research workflows in an easy to package and deploy and access way. So what it does is it goes through a few layers, and it's built, again, kind of same pattern, as reusable tools, each of which does one thing. At the bottom, there's something called Repo to Docker. What Repo to Docker does is a tool that takes a GitHub repository and spits out a Docker container. So if you give it a GitHub repo, you will get a Docker container. Then there's Jupyter Hub. Jupyter Hub, the Jupyter Hub you are using is used in Binder to give you an interface to access that container so that you can actually log in and basically connect to that container that got built from a repo. Then it provides an interface to create and share these live sessions. And finally, we actually have a web service that gives you free compute and that lets you run these computations on the web. Now, obviously, this is limited. They're teeny machines. You're not going to run big computation. But the point of this is currently funded by the Gordon and Betty Moore Foundation. The point of this was to get enough of a demonstration to show the value of these ideas so that over time we can look for a model that can make this scalable. And we'll get to that in a minute. So I want to take a bit of I'm a physicist originally, so I like this example because it brought a lot of satisfaction to us in the project. In 2017, the Nobel Prize in Physics was awarded for the team of 3 scientists who led the discovery of gravitational waves. Gravitational waves were a prediction made by Einstein in 1916. Einstein predicted this is the basic field equation of general relativity, which predicts that masses that move in space-time, masses that accelerate in space-time, will radiate energy, just like electromagnetic. The acceleration of a charge will radiate energy, and it's called light. This is due to the acceleration of electric charges. The acceleration of masses will radiate energy in space-time, and that energy will travel as a wave at the speed of light. That c is the same speed of light. And so Einstein predicted that if there were massive events of accelerating mass in the universe, there would be ripples in space-time that would travel through the universe. It turns out that the detection of those is a spectacularly difficult technical problem. It's a phenomenal feat of engineering. The way to detect these things was to build 2 instruments. We're not very far from one of them. One of them, this one right here, is in Eastern Washington. We're right about here, and it's over here at a place called Hanford in Eastern Washington. It's very nice and flat. And the other one is down in Louisiana, here in Livingston. And the problem, these instruments look like this. They are 2 4-kilometer long beams where you shine laser light like this. Where the two beams meet, you shine a laser and you split the laser. And half the light goes this way, half the light goes that way, and it bounces back on a mirror and comes back. And since laser light is coherent, all the photons, basically the electric field goes up and down at the same time. If everything is happy and static, they go and they come back in phase, right? If a gravitational wave comes by, remember, space-time itself is what's stretching. So one of them goes up a little bit and the other one goes like this, right? So they stretch out of phase, and you will see that change in length in these tubes as a shift, as an interference pattern between between these photons that ought to be in phase. Now they come slightly out of phase. Slight problem. You're trying to detect a change in length of roughly 1/1000th of the diameter of a proton over a distance of 4 kilometers. That's about 10 to the 21 in terms of sensitivity. You have about 21 orders of magnitude. To give you a sense in terms of imaging, to get you a sense of scope, this is sort of like looking for an object of about the size of a person, like a meter, say order of magnitude, a human being, in a photograph, but not a picture, say, of this room, not a picture of Seattle, not a picture of the Earth, but a picture of the Milky Way. So you're looking for one person in the Milky Way. That's the problem that these people were trying to solve. It took about 30 years to build this. I remember when I was in grad school in the 90s, I saw a talk about the building of LIGO, and I remember a colloquium in the physics department. I thought, these people are crazy. They need to be locked up. You can't do this. This is nuts. Experimentally, instrumentally, right? You cannot do this. A truck going by miles away creates a signal orders of magnitude bigger than what they're looking for. They need to correct for the motion of the moons of Jupiter around Jupiter in their signal on Earth, right? That's the level of correction. That's why it took 30 years of building. After 100 years of theory, it took 30 years of instrumental building to get these instruments to work. And if you click on this, you get to the LIGO Open Science Center. And if you click on this, you get to Binder. And if you click on this, you're actually looking at the notebooks that run the entire analysis with the real data of the real events. First event, which is called 150914, they observed the merger of two black holes of roughly 30 solar masses, give or take, that were spiraling into one another. And as these two black holes spiraled into one another, about 1.3 billion light years away, they radiate energy. And that's that first event. After that, they've had a few others. And the point is, 100 years of theoretical physics, 30 years of building instruments, a collaboration building these tools with, building this analysis with these open source tools. And here, with one click of the mouse, this is running off of the LIGO Open Science Center. This is running on Binder. Any of you who clicks that link can be actually running the analysis of the LIGO collaboration. So this is the point of actually making science available to someone else. By defining how to package this, by building all of this infrastructure, all they have to do is put their stuff on GitHub and follow these standard practices that, yes, they do take a little bit of learning, but they can be taught, not just to giant, massive, billion-dollar physics collaborations, but they can be taught, as I showed you, to undergrads in stats in a few months in class, and then you can provide your research to others in a way that allows them to grab it, run it. We're running the real code. This is not pre-computed. I just clicked run and I ran it. We can change any of these cells. We can edit it. We can do whatever we want. We have an actual live notebook environment. We can ask questions about, is this data correct? Are they doing the right thing statistically? Do I want to run this with new data, etc.? We even have, let me find where they are. This is the signal that made it it's a little bit easier to hear here. Did you hear the whoop at the end? That little whoop is this, which is the plot as the two black holes accelerate in real time. The only thing that's been done to that is slightly frequency shifting it so we can hear it a little bit better. The actual data is at very low frequency, so it's kind of hard to hear. But other than that, that is actually the sound, meaning the strain on the vibrations turned into sound of two black holes 1.3 billion light years away, merging into each other, sending ripples in space-time. And this is the measure of in this case, the Hanford data against the black line, which is a numerical simulation of what that should look like. The amount of statistical fishing that has to happen here is pretty substantial. I mean, in addition to the main paper that they published on this result, there were like 20 papers or so on all of the statistical machinery. But the point is, with this, you can make it. They can make it available to us. You can make your work available to others. And all I had to do was click a link. That's it. A browser, a link, click on it, and we're actually running that code. And we're making that work available to anyone who wants to see it. And so I think we do have an argument here. We do have an argument here that with these tools we are getting closer to sort of embodying this idea that Donahoe and his colleagues proposed over 20 years ago of packaging our work in a way that is available to others. As I mentioned, it began with the work from Jeremy Freeman's lab after a discussion we had, basically saying we have all the tools to do this thing that Donald's been talking about. And Jeremy went and with folks in his lab kind of came out with a prototype early on that put it all together. And now the Jupyter team has sort of picked up his early prototype and made it into much more robust infrastructure. This is an actual screenshot of the first figure in the main physical review letters of that paper about that discovery. One thing that was very satisfactory for us is that this is probably going to be one of the most cited results in physics for the next 50 years or so. This kind of opened up a whole new way of doing astronomy for the first time in the history of humanity. We've had up until now, astronomy was basically a one-channel science. You were looking at light, because radio and X-rays and everything, it's the same thing, it's light, right? And then for the first time in history, we have a second channel to do astronomy. We have gravitational astronomy, not just light astronomy. It's a fundamentally different force of nature that we're doing astronomy with. And all of this stuff was done with open tools, right? These plots are NumPy, Matplotlib. The color map was actually developed by neuroscientists and NumPy developers. This was an open source development for a better default color map with better visual perceptive behavior that was done a few years ago with work from folks at Berkeley and the rest of the Matplotlib community. And for me, it was immensely satisfactory to think that we, as open source scientists in other disciplines, can contribute even a small part to this kind of effort that this team builds up. So internally, Binder has repo to Docker. So I want to tell you a little bit what the pieces are. just so you have a sense of what's happening under the hood. But as I mentioned, the idea is when you're using this in practice, you don't need to know all this. You don't need to do all these things. Some of you may be interested in this machinery if you want to extend it in new directions, but by and large, you can use it as an existing tool. So repo to Docker, you give it a repo, it builds a Docker image, it will take things like that environment YAML file that I showed you already a couple times, or equivalents of it for other languages, and it will package it up into a Docker image. It's fairly tightly scoped, and this is important, I've already mentioned it. It's not meant to build any Docker container for anything so that you can build your new startup with it. Go do that. There's a lot of people doing that. This is really for packaging sort of analysis workflows in an easy-to-go way, the kinds of things that we do as scientists to give them to others, just like I showed you with that. So you run repo to Docker against the repository, and then it goes and basically does all of the steps that normally you would do as a person, which is you would clone the repo. It will look for, oh, what are the dependencies, right? What do I need for this code to run? I need a requirements file. It also recognizes environment YAML files. It recognizes R requirements. It recognizes actually many, you can specify what the dependencies are in many ways. It will then set up the environment running, these are Docker commands. It will assemble the whole thing, and it will produce what's called a Docker file. A Docker file is a script. It's not the Docker image file. Remember I said Docker is a way of basically having a file that is like a computer packaged in a file. That's called the image file. It's a big binary blob. This is the script that makes that thing. And then it actually makes that thing. It makes the image, it builds it, and it pushes it to a public, just like we have GitHub for Git repositories, there's something called Docker Hub for these things, for these images to be built in public so that they can be available and cached up there in the magic cloud, and you can refer to them and find them after the fact so that you don't have to build them every single time. So it does all this. So as you do that, currently it understands these requirements for a variety of languages, the Python standard, the Julia standards, the R standards, the Linux one for apt, or you can build a raw Docker file yourself. If these are basically saying if the basic stuff that it does is good enough for you and you just need to add a few packages, you can tell it what packages you need. Or you can give it a raw Docker file and say, I need to build it from scratch, start from scratch. You have to be a little bit more careful when you do that because you have to follow a few specific conventions. So you end up with a working binder Docker container, not just some random thing. But you can also you do have full low-level control. And so you can build Python environments. Importantly, you can run any UI. Remember I said you can't package a GUI inside of Docker. You can't package Microsoft Word or Photoshop in there, but you can run anything that will open up a port for a web browser to connect, which means it's not just it uses Jupyter machinery, but you don't have to give your users a Jupyter view at the end. If you choose to, you can have an RStudio view, you can have an open refined service, you can have some other service that makes sense for you. That's totally fine. And once you have it, you run it with Docker, either locally or in the cloud. That's up to you. On top of it comes Jupyter Hub, which is the thing you're logging into. What Jupyter Hub does is it lets you authenticate. Remember how it checked when I was logging in? You probably all had to do that. You it checks with your GitHub credentials and you say, yes, I want to authenticate with GitHub, and you connect in. And then it has, Jupyter Hub is a service that has something called a spawner, which will start a process. So once you get in, it will run the process, the actual computation that you want to run. And what Binder does is it takes Jupyter Hub and puts on top of it Kubernetes. Kubernetes is open source machinery developed by Google to basically manage these containers in the cloud. So it's a very, very sort of DevOps engineering heavy project, but the Jupyter Hub team and the Binder team have basically packaged it for these scientific workflows in a way that you can mostly not have to know too much about it. I think Ariel right now is pretty deep into Kubernetes. I suspect that's what you were looking at, debugging these things for the hub. But ideally, they have packaged this so that for a scientific workflow, it's just magic up in the sky. And so the way it looks is when you go to Binder Hub, you have a web interface where you tell it, this is my repo. And as long as your repo follows those conventions, remember I said, you have a repo, you tell it your dependencies, you have either a conda file or an environment file or a pip file, whatever, as long as you follow those conventions, it will grab the repo and do all that for you. You can actually choose to create the repo from a specific branch or from a specific commit or tag. If you want to say, oh, for the paper, you make a tag. You're working on the project and you say, this is paper submission. Okay, make a tag it, and you can have a binder for the paper submission. Then you can have a tag for the paper dash published. And that way the reviewers can imagine if you're reviewing a paper and you get a binder link. I've reviewed papers where the authors have tried to provide some code and data, and I start installing stuff, and after 2 or 3 hours I hit some weird roadblock, and I said, you know what? Enough. I'm doing this for free. It's Sunday night. I've already wasted 3 hours installing their dependencies. I've run a few things. I'm not doing this anymore, right? I'm going to just keep reading the PDF, and I'll do. What if you gave me, as part of the review process, this is the PDF, and this is the binder link, and I'm reviewing the live, real analysis, and I can change it, and I can wonder, I wonder how sensitive their stuff is. I wonder if I move this little parameter a little bit over here, will that result survive or not? I don't have to ask them. I can make the change right there. I wonder if their method is really as robust as they say. I have a little bit of data kind of like that. Let me put it in there and rerun it again, and let's see what happens. We could do that if we had a link like this. I'm not going to do that if it requires that I spend days or weeks installing stuff from scratch. And so once you do this, you get back a link, which is that link that they had on the LIGO page, where you click on it and boom, it takes you to the live executable version. And so let's kind of skip these technical details. This is basically what's happening under the hood as you go through, and Jupyter Hub talks to Binder Hub, builds the image, pushes it up, and then creates a pod. At the end, the point is you have these services. We have also this service that we run as a demo. This is where I just logged in to run the LIGO one. Right now, the Jupyter Hub that you're using is run by Ariel and the local team. It's a specific private one. Binder Hub my binder is completely public. You can put anything you want. People are using it to demo. Basically, you want to give a demo of any one of your software, just give them a binder link, and that's it. They can click and they can run it, which means, and since you can have Jupyter Lab with a terminal and with everything, they have a terminal. They can, as long as it can run through a web interface that includes a terminal, you're good to go. And it's not limited. You could have in there a big C++ compilation blob. You could have a big Java, whatever. You can have a database. It doesn't matter. The hardware that we provision is relatively limited. They're basically the smallest and cheapest virtual machines that we can provision. So it's not like you get a supercomputer there, but you do get something to demo pretty much arbitrary computational processes to people. One thing that we're really happy is to see the growth. The growth has been huge by orders of magnitude as the project has been cleaned up and been turned more scalable. It's growing not only very rapidly in usage, but geographically. And for me, this is a really, really important plot. Chris and Min in their talk at SciPy were emphasizing this, but for me it really means a lot, is the fact I come from Colombia. I did my undergrad. I was born and raised in Colombia. I just got there from there 2 days ago. One of the motivations for me when I started doing research with open source tools back and building things like IPython was also to say, I want to be able to share back with someone like my former advisor in Colombia, who doesn't necessarily have the budgetary freedom that I have at a big fancy US university where we have licenses for everything, to be able to share my work with him without any constraints and without any barriers, or without asking him to either spend a huge amount of, relatively speaking, a huge amount of budget on licenses or pirate software. But just using open source software, there still are barriers to access. I think this is basically about as low of a barrier as we can make it. That binder link, as long as a person has an internet connection and a reasonably modern browser, they can run that stuff, right? Those are the two demands. And today in the world, I know there are parts of the world that don't have water and sanitation and whatnot. So I'm not saying we're covering every human being on the planet, but an internet connection and a basic web browser, that's already accessible to a lot of people. That really is a lot of people. A lot more people than the people who could access scientific research 20 years ago when it was being done, when you had to have the data and the hardware and the big compute and the proprietary software all locked up in one lab at a few big universities in the world. And so seeing this really reaching, including, sure, the coverage and usage density is higher in the US, and these are Google Analytics data, which is relatively coarse, but the point is almost the whole world is kind of blue. There's a few countries in Central Sub-Saharan Africa that are not registering, unsurprisingly, some of the very, very poorest nations in the world, but we do have a huge amount of coverage worldwide, and to me that's very satisfying. If you want to know anything about what's being done, go to the Grafana website, domain on Binder, all of the runtime data. It spits out, all of the analytics are open because we're running this as a very open project. Part of it was designed to, we only got about a year of funding from the Moore Foundation to do this, and the point was to instrument it extremely heavily to learn what does it take to do a service like this, so we can learn what are the costs, what are the infrastructure demands, what are the usage patterns for this to hopefully grow and scale as something that exists in other places. So there's statistics on a lot of stuff. The cost per user has been going down, so it's been getting better and better and better. They've been optimizing a lot. And so now what we're thinking about is, okay, well, when the money runs out, which is very, very soon, and I need to be writing a grant very soon, how do we sustain this? And one of the ideas that we're thinking about is how do we federate this? From the very beginning, we never imagined we're going to run the binder, but rather, can we take this as a model that is replicated and used everywhere? Can you imagine saying, if you have a PDF, you can go, let's say that you have a subscription to the journal, you can read the PDF on the journal website, but you can also download the PDF. If you want to read it on your phone, on your tablet, you want to print it, and read it on a piece of paper, that's all okay. Can we get to the point where we have the moral equivalent of that, and you say, oh, I want to run that binder, but I want to run it on my cluster. I want to run it on my university, gives me big resources. I want to run it with my cloud account. I want to run more than the little demo. So ways of federating, and again, back to the same stories that I keep telling you about, things like the open standards that we used for Jupyter and the languages and whatnot, standards for defining how to federate and how to access these resources so that this can be driven by the community. There's technical growth in support for more tools, for more languages in repo to Docker, so that it's easier to package workflows based on other tools. We're very interested in talking to folks also on the scientific publishing side of things, and that's continuing to happen. There's still open problems. If you have a huge data set, it's not going to fit in there. So what happens if the container runs and then the gigantic multi-terabyte data set isn't available anymore? How do you deploy these ideas if you need to run on a big supercomputer that has its own scheduling system? And it turns out that supercomputers and large HPC facilities are really complicated environments, but we are working with those people. And I think this matters. I want to note the date. This is very, very recent, and this is a statement that was put out by the German. This is an organization of German universities, which for the last, I don't know how long, I think a year or so, they've been fighting with Elsevier on better terms for access to the scientific literature in Germany that are not as predatory to the German research public budget as they have been in the past. And basically a few weeks ago they kind of published the statements pretty much saying this is breaking down. Like the terms that the publishers are demanding are simply not sustainable. We cannot, in good conscience, as the German government and as the German university system, accept these terms. And they're kind of basically saying this is unacceptable for public research. And what we want with the development of these tools is basically to contribute to scientists having more weapons in this fight. Because on the other side of that table sit people like Elsevier with a ridiculously large budget and extremely predatory behavior towards the budgets of science. And we want to provide something that counters that. So, thank you so much. This is basically dead on time. I did go slower than I was intending. My plan, if I had gone faster, but I think it's okay to have done this, was to, let's see, where is it? I think I have it here. Yes. Was to basically try to take you through the process of creating a toy version together of what I showed you from the class, kind of saying how do we make this happen together, of creating a toy repo that has data, that has code, that has tests, that has analysis, that has a main narrative, but we didn't get to it. I actually kind of decided deliberately to slow down rather than trying to ad-lib this crazy, because I haven't tested doing this live in about an hour, and so I decided to forego that. If anyone is interested, I can post. This was the instructions for that project that I gave to the students. What the students got when they were asked to do that was an empty repo that had a README. The README itself was empty because the idea was that would be their README. They would write the README about their analysis, and there was simply an instructions file telling them all of these things that I outlined for you. So I was thinking of trying to do this live, but I deliberately decided to instead cover the rest.
Python packaging tutorial after lunch will go over some of these things in a slightly different direction, but some of these things will go hands-on into some of the things that Fernando mentioned in structuring these projects. So we'll take off from
some of these things. But otherwise, we did cover everything else that I had in mind. Thank you so much. We're right at noon. It's been a lot. I don't know if there are questions. There were not a lot of interruptions. I don't know if I've been kind of hammering too much. But if you have questions either now or over lunch, I'm going to be here until Thursday. So anytime, the whole point of me being here is to talk to you about these things, to answer questions, to sit down with you and work, etc. So thank you so much for your attention and patience. I hope this was useful. And I don't know if there are any questions, or we just go for lunch and I can talk to people after. It's up to you.
So let's take a few minutes for questions if people have any more questions.
You've already asked, so I'll get back to you later. Yes, question.
What do you think of Sci-Hub in relationship to
Sci-Hub. So the question is, what do I think of Sci-Hub? Sci-Hub, I think, is wonderful, but Sci-Hub is effectively kind of scientific anarchism against the behavior of these publishers. For those of does everybody know what Sci-Hub is? No. So Sci-Hub, for those of you who haven't heard about it, is a project actually started by I think she's a neuroscientist, right? Alexandra something in the Ukraine. I don't know her last name. She's a grad student, I believe, in neuroscience in the Ukraine, who started a project to basically post PDFs of any paper in the scientific literature. She's been building a giant database, and they actually encourage people to post, if they have credentials and passwords to login links, to post either the PDFs or the actual logins, so that basically you can search for a paper and they will download it and cache it and give it back to you. Obviously, the publishers absolutely hate them. They've been chasing them up and down the internet. They've closed their hosting. They've shut down many of their domains. So, I mean, I love what she does, but I don't think that's a sustainable solution, because what they are doing is illegal, right? And it is illegal, which means in many jurisdictions they will get shut down. In many places the domains will get canceled. They won't be accessible. I think what we need to do is, I mean, I hope she sticks it in the eye to them, but we do need to change the terms of this conversation also on legal terms. And that's what I'm trying to work with, is basically building tools that give the scientific community tools to kind of push back against these publishing monopolies on legal grounds. You first.
So as a TA, you try to teach kind of GitHub and Python to students before. I'm curious, what were the requirements that the students had to take before actually trying to learn this, or do you have a strategy of easing them into this method?
So what the question is, what was my strategy kind of easing them into Git and Python, these things? We kind of taught, I gave them, Jake Vanderplas has a little booklet called The Whirlwind Tour of Python, and we covered that at the beginning. So I assume they had to have some programming background, but we did cover very quickly Python at the start, and we did do a tutorial on Git. I have a different take on teaching Git than many people. I have a little tutorial that I wrote for Git that basically tries to actually implement Git. You implement Git in about 5 lines of Python, You can, it turns out. It takes about 5 lines of Python to implement Git, and you show what the core ideas are of Git in terms of what it's doing conceptually under the hood. And then on top of that, later people, I think it becomes a lot easier to go and search on Stack Overflow, because I can't remember things either. But by teaching them the core conceptual ideas of what Git is doing internally, I think once they have that mental model, and then they use it as an everyday tool, because we do it from the start, we teach these things right at the beginning, then it becomes easier to kind of say, well, this is how we work, and we bake it into the workflow. And then the projects are actually domain specific, and they have to analyze new data, and they have to do the homework on GitHub. And I mean, all I can say is it seems to have worked. By and large, the student response was quite good and quite positive. Before I get to you, Chris, because you've asked me a few questions already, I want to get to you in the back, then I'll get to you.
Do you have any journals that are
JB, do you want to answer that?
I mean, I know of eLife as a tool now working with Jupyter, which is basically something that is based on the ecosystem. And I know there's another one. I mean, they also have Stencila, which is a bit of a different flavor of development. So eLife has been
Yeah, and we've had a lot of conversations with the eLife team, and part of it was getting to this point, building the technology. The first version of Binder was really very much of a proof of concept. It was completely non-scalable. Jeremy was paying literally out of pocket, well, grant pocket, but out of his remaining Janelia farm grant. Even when he wasn't at Janelia anymore, the system had no scalability, so there was this kind of first, we had to do this engineering, and it was deliberate, very deliberate that we did all that instrumentation to measure those costs. Now that we have a year's worth of data of what does it cost, it's a lot easier to go, I'm not so interested, in case it wasn't obvious, in helping Elsevier, but going, for example, to the nonprofit publishers and the professional societies and say, hey, this is what first of all, the infrastructure is there. Many professional societies don't actually have a lot of technical staff. So this has been packaged, and it kind of works, and these are the costs levels and the cost impact. And then you can have, and we are beginning to have those conversations with professional societies. For example, the American Geophysical Union has been doing work in publishing in this direction, and SciAm, the Applied Mathematics Society, they have been doing work kind of in these directions, and I'm hoping to engage with them in the future. But we needed first to have something that was technically functional and also some data on what does it cost, because otherwise you're having these conversations kind of in a vacuum, and these organizations are, as everyone else, already stressed and overtaxed, so it was too big of a gap to engage. But I think now, with a viable foundation and data on what it looks like to run this stuff, I think we can start having those conversations. Okay, now to Chris.
Okay. So I was looking at the graph of like user growth that you presented, and noticed that in the beginning it seems to be like a jump that was like capped, and that's probably because you just limited the resources. And I wonder if what we're seeing right now, those around 10,000 active users, is that something that is with reaching the cap?
Yeah, we have caps. Yeah, we have a cap. We have a cap of $6,000 to $8,000 a month because I mean we were getting grant money, so we wanted to spend enough to have like realistic data, not just a toy with 2 or 3 people. But we couldn't really get a grant and say we're going to spend $5 million on giving free compute to everybody in the world. And so we chose a number around $6,000 to $8,000 a month.
The actual popularity of the service
could even be higher.
Way higher.
Yeah, it could be higher, and so we need to get there. If you have $10 million burning a hole in your pocket, by all means. There was another question.
Yeah, you said funding was going to run out soon. How soon?
A few months.
Okay. So don't like build a class in the winter that relies on this.
Not on Binder, but run your own.
Yeah.
Deploy your own. But now and Binder is definitely a demo service. It's not a critical reliable. The terms of service of Binder are best effort, good luck. Right? That's it. That's what they are.
But I would say if people are interested in how to set up something like what we set up for this, which might be a better match to a class, right, where you need people to go into the same machine again and again and do stuff. Well, we can find a time to sort of go over that infrastructure. It's actually fantastically documented. So
and it's
pretty much all I'd have to do is send you a link to a website, which I'll Slack in just a minute, and you just follow those instructions. And you can talk about it.
And it's using the same pieces, right? It's just not the one that runs at Binder, right? That's all. People have run little workshops, and with a little bit of talking to the team, like, hey, can you reserve a few pods for a few hours? It's been done, but we can't do that in a scalable, in a scalable fashion. And importantly, what Ariel just said, Binder is not meant to return to it, right? These links are ephemeral, so when you disconnect, it goes away, the pod goes away. So you can play with it, but if you want to make persistent changes, you have to copy it somewhere else. And so for a recurring course, it's not meant to be a good solution. Kirsty.
So Jupyter has been really widely adopted in industry, in banking, in all of these different areas of data science, way outside of academia, which is obviously the stuff that you've come today. Do you have a way of sort of how do you evidence that sort of spread, and how much people who are not getting academic sort of rewards, how much they're using your tools?
It's an iceberg. We can only evidence the parts that we see publicly. And some of those are very visible. And for example, we use those in our impact reports and our research reports and our grant reports. Amazon SageMaker is based on Jupyter. Their new machine learning powered hardware camera, the tutorials are based, like the hardware connects to the models are trained on SageMaker and the tutorials are on Jupyter. Like, look, Amazon's doing this. Google has Collaboratory. Azure, notebooks.azure.com or is Microsoft. So we can show all of that. We know, we have a glimpse of the iceberg because of the security. We have a private security mailing list where we discuss privately, and it's invitation only. We actually check who's asking to be invited. And we know from the email addresses where those people are coming from. And also we talk to people in industry, but that's only a glimpse of the iceberg. It runs a lot deeper, and people, there's no phoning home code in there. There's no licensing requirements. That is the flip side of open source. It is open to anyone to download and use as they see fit behind the walls of their organization, completely in private, and they don't need to tell us. So when they feel like telling us, or they end up telling us because they send an email to the security mailing list, like, it's interesting that that email address is there. We see a little bit of that, but ultimately there's a lot we can't see. It's probably a good time to stop, and I've been talking a lot, and I'm sure everyone is tired of hearing me and hungry, but thanks for your attention, and feel free to come to me for any questions you have.